we would like to start our fourth talk of the day and our last talk here. So just before introducing the speaker, reminding you, right after this talk we will go downstairs to take a group photo, and that the next talk will be at the math department colloquium at 2:30, trying to make it 2:35 so you'll have enough time to eat, or eat on the way. So with that being said, so I'd like to introduce Dor Minzer, who will tell us about recent advances in PCP via high-dimensional expansion.
Okay, so hi everybody. Is it working? Does it work now?
I can make it stronger here, louder here.
אפשר מיקרופון? דבר רגע אותה? עכשיו זה בסדר? אוקיי. I think that now Okay, now it's fine. Okay, so hi everybody. Thank you for staying until the very end, and thank you for the invitation. So in this talk I'm going to talk about how Alex has influenced my work. I'll say more words about it roughly in the middle of the talk. So I apologize in advance. I'm not going to say the word group a lot. In fact, I'll say it once and that will be it. But still there are groups in the background. So I'll mainly talk about...
And the title of the Midrasha is Groups, Expanders, and Codes. So.
Yeah, so that's why I put this other work here. So I'm going to primarily talk about the sequence of works with Mitali Bafna, Noam Lifshitz, and Nikhil Vyas, and also Zhe Zheng. And then in the end I'm going to tell some more recent implications to our algorithmic code. So what is this talk about? So it's about PCP, so let me tell you what is PCP. So the genesis of PCP is 3-sat. So we talk about formulas. A 3-sat formula is a formula of this form. You have variables x1 to xn, and phi is equal to n of clauses. Each clause is an OR of 3 variables up to negations. And the computational problem associated with it is I give you a formula and ask you, is it satisfiable? Can you assign Boolean values to the variables so as to satisfy all of the clauses? And this is a very important problem in computer science because it captures the complexity of this big class NP, which contains many problems that we care about, in the sense that if you know how to solve 3-sat efficiently, then you know how to solve the entire class NP efficiently. So it's enough to focus on that, and this is indeed something that people have done. And for the sake of this talk, I would like to take a slightly different perspective on this decision problem. I'd like to think about it as a verification problem. I give you a formula phi, and I give you some extra information, a witness. This witness is supposed to help you to check that phi is satisfiable. How can you check that phi is indeed satisfiable? Well, in this formulation, it's very simple. The witness can just be how to assign all of the variables. It can just be Boolean assignment to the variables. And then your verifier is just going to go over the clauses one by one and check that each one of them, at least one of the literals, evaluates to 1. So that's very simple. But this verifier is not really efficient. So we've already given it a lot of information, this entire witness, which is hard to find. The very least would like it to be more efficient than just reading all of it. So in particular, this verifier reads all of the witness, it reads all of the assignment, and there is a question of, is there a more efficient verifier that pretty much does the same task? Okay. So let's go towards it slowly. So first of all, if you talk about deterministic verifiers, there is not so much you can do. So the first thing that you do is you relax yourself and say, okay, I'll talk about randomized verifiers. I'll talk about randomizer that can flip coins, and based on it, decide what to do. And here is a very deep verifier that you can do. Well, you still get your formula, you still get a witness which is an assignment, but now instead of going all of the clauses, you just choose one of the clauses at random, you check that, if it's satisfied you're happy, otherwise you reject. So now this is much more efficient, you only read like 3 locations from the proof, it's a very deep result. But of course you are not very happy with that. So why is that? Well, if phi is satisfiable and I did give you a correct witness, then the verifier will always accept. It's easy. But if not, then all I know is that W fails to satisfy one of the clauses out of mn. So all I can say is that the verifier accepts with probability at most 1 minus 1 over the number of clauses. So this is much more efficient in terms of how many bits I read, but this gap between the good case and the bad case, it's very tiny. It's 1 over m. You wouldn't bet your life on this distance. So the soundness is very weak, and the question is, can you improve it? Can you get something that has substantially larger gap between the yes case and the no case, while still retaining the fact that your verifier is efficient? You only read a handful of locations from the witness. Okay. So this is where PCP comes into the picture. So this is a really great result. It is the following statement. It says, there exists some completely different verifier, which I'm going to refer to as V sub PCP. Now that verifier gets as input 2 things. It gets the formula, just like before, but additionally it gets some witness W. And this witness W is no longer some nice assignment. It's potentially longer string, which I couldn't describe to you even if I wanted, because it's quite, so I taught the proof to this theory in my grad class, and it took me half a semester. So it's not very simple. So the verifier takes these 2 things as input, and it has the following features. So first of all, it's only going to look at 2 locations in W. So you only read 2 locations in your proof. And if phi is satisfiable, then your verifier is going to accept with probability 1. Just like before. If there is a correct proof, you're going to accept with probability 1. Now on the other hand, if there is no satisfying assignment to phi, then no matter what W you give me, the verifier is going to have noticeable advantage, or disadvantage. It's going to accept with probability at most 0.99. So now we have a constant gap between the good case and the bad case. So this is something already much more substantial. And this is a great result. You can do many things about it, or many things using it. It has many applications in hardness approximation, cryptography, and lots of other places. And I would like just to mention a few things that will be of interest to us in this talk. So first of all, there is this little bit of technicality. So I wrote here the alphabet as sigma as opposed to 0, 1. That you should ignore. If you want, you can think about it as 0, 1. It's just that if I want to be really honest, it has to be at least of size 3 for the statement to be true. So that's one aspect, you should ignore that. Secondly, you should notice that this witness now, it's polynomially larger than the previous witness. So usually in computer science, this is good for us, like polynomial is nothing. So that's a good aspect about it, but it's not great, as we'll soon complain. And thirdly, the soundness here, the key feature is that it's bounded away from 1 by a constant. So it's not ideal, but it's really strong still. Okay. So as I said, this is a very powerful result, and you could do many things using it. But in life, whenever you have something, you always say, okay, that's good. Let me complain about it and try to make it better. So now what I'm going to do in the next slide is complain about the PCP theorem. And these are not my complaints. Like, people have complained about this for a long time, and I've worked on it. And so I'm going to complain about two of the aspects of this theorem. So first complaint is, while it is good that we have constant gap between 1 and 0.99, I hope that you still would not bet your life on this little bit of gap. So you could hope for better sounds. You could hope that if phi is unsatisfiable, V accepts will probably at most 1%, or even smaller. So that's already would be quite nice.
Just repeat, or okay.
He forces two queries. That's kind of a must.
Yeah, so the answer to both of these questions will appear in one of the slides. So we'll get them. Remember, there is HDX somewhere in the picture, eventually. Second point that I would like to complain about is the length of W. Well, it is polynomial linear, and I don't really know what is the polynomial that the original proofs achieved, but you could hope it to be smaller. Ideally, you could hope it to be linear. And you'll have to take my word for it, but this is not just I'm coming up with two parameters and telling you improve that. Once you manage to improve these lead to direct implications in a whole bunch of areas. I gave a few examples here. I'm not going to give you any concrete application, but you'll have to trust me that it exists. Okay, so these are my complaints, and this is what most of the talk is going to be about, of how to go around it. Okay. So let me tell you about previous works. So, of course, when you have sound 0.11, natural thing is try to repeat it. And as it turns out, there are two ways to repeat your verifier. There is something called sequential repetition, which we'll see, and something called parallel repetition. Each one of them are good or bad in different aspects, but this is a generic tool that allows you to reduce sounds. And this is originally new to us, and then it was improved by a bunch of other works. So this tool by itself can reduce 0.99 to be any number, like 1%, 0.1%, something like that. But it cannot give you soundness which is vanishing with the instance size, like 1 over log n or something like that. If you want that, you need to do other things. And there is a distinction between these two bullets here, which I just mentioned that this bullet refers to PCPs with more than 2 queries, and these PCPs refer to 2 queries. Typically, we want 2 queries, so this is why these results are very important, but if you allow more, you can get better results. Okay, so that's what we've done about improving the soundness of a PCP. Now, about the size, so shortly after the PCP theorem was proved, Polisukins-Feldman showed that actually you can get the size of your witness to be almost linear, in the sense that for every epsilon, you have a PCP of size n to the 1 plus epsilon, but it doesn't come from 3. So the soundness parameter, this 0.199, it somewhat deteriorates as you take epsilon smaller. So you get something small, but you pay for that in the soundness. In incomparable result of Benson and Sudan, they managed to drive this down even further and get like almost linear. So I'm going to refer to this as quasi-linear. They managed to get n times polylog n size. And the soundness now is even slightly worse. It's even closer to 1, but it's still a highly non-trivial soundness. It's 1 minus roughly 1 over log n. And then in the proof of the PCP theorem, Irit managed to sort of get the best of both worlds of both of these results. She managed to get quasi-linear size while having the soundness being at most 0.199, some absolute constant bounded wave from 1. And lastly, if you actually look at this work that I already mentioned of Moshkovitz and Raz, you will see that they get a slightly larger PCP, but their soundness is even smaller than Irit's. It's epsilon arbitrarily small. Okay. So these are the previous works, and to sort of set up towards what we're eventually going to do, I want to tell you a little bit about parallel repetition, how it actually looks like, and then complexes are going to appear in the background naturally. Okay. Any questions so far? Yeah.
In Moshkovitz graphs, the epsilon doesn't get into the side or somewhere else?
So actually, you can take it to be subconstant. It's 1 over log or something like that.
But it doesn't affect the size?
So instead of this epsilon, you can think of it as 1 over some log, so it's like vanishing with them. Okay. So let's talk about parallel repetition. So here is a problem. We have this black box, we have this PCP verifier, and we know that if you give it a formula and the formula is unsatisfiable, then no matter what witness you give it, it's going to accept with probability at most 0.99. How can you produce a verifier that does even better in terms of soundness? So one thing you can do for sure is just run VPCP once. If it accepted, go on. If it rejected, reject. Now run it again, and again, and again, and again. Run it for k times. So you can see, and this is very easy to show, that the soundness will decrease exponentially in k. It will be 0.99 to the k. So done. So not quite done. So if you look at this VPCP, or the one that we repeated, eventually it's going to read 2 times k locations from the proof. So somehow it's becoming less and less efficient as we increase scale. And for applications, it's often very important that you just make 2 queries. So this does not give you anything in terms of if you want 2 queries. So what can you do instead? So how do you amplify the soundness without increasing the number of queries? And sort of the idea here is you have these 2k questions. Why do you have to ask them separately? Why can't you just look at a single proof location that will give you much more a single query? So let me make it a bit more precise. So this is called, so far what I told you about is called sequential repetition, because you do it time after time. So instead of that, you can apply what is called parallel repetition. So in a picture, it looks like that. So suppose you have your PCP verifier, VPCP, and this is its witness, W1 to W sub n. Now, what I want to do now, this is my tensored verifier, I want to think of a new witness, which is much longer. It's of length roughly m to k, so I'm just going to call it m to the k because it doesn't matter. And each location in this new proof is going to correspond to k locations in the original proof. Okay, so like each point here, you can think about it as a subset of m of size k. And the symbol that you're supposed to assign here is what we did the symbols of the witness in these prescribed locations. Okay, so that's the idea. You make the witness much longer, and also each.
Also the alphabet size.
Yeah, right. And the alphabet size is also much longer because each symbol here is telling you k symbols from the original thing.
Why is 2
So you have to see how this is used in reduction, but it's often useful to think of like the PCP verifier as acting on a graph, as opposed to hypergraph. So, okay.
But though,
Mhm.
earlier you read 2K bits,
Mhm.
and now you're reading 2K bits. So it's alphabet group.
It's 2K bits, but it's two alphabet symbols.
Two?
Alphabet symbols. So I'm okay with increasing the alphabet size.
Sounds like cheating.
Yeah.
It's not the amount of information you read, it's how many times you ask to read something.
It's how many evaluations of a function you are making. It's not how much, exactly as I did. It's not the amount of information, it's how many queries I make to the function. Okay. Yeah, I mean, I agree that it looks a little bit like cheating originally, but it's not. And actually, if you try to prove that this thing works, you may say, okay, so if I sample my two locations, it's like K test of the original thing, they're sample independently, so it's clear that it works. The original paper that suggested it had the same idea. They said, it's clear. It's not clear, and it's false. So it's false that it's like rough, that it's multiplying simply. And actually, it's a quite difficult proof by Ran Raz, and he showed that it is going down exponentially if you do this parallel repetition. So Raz proved that, well, for this you don't need Raz. If phi is satisfiable, then this new PCP verifier accepts probability 1. What is completely not easy is to show that if phi is unsatisfiable, then this tensor PCP accepts with probability exponentially decaying K. Yeah. So that is parallel repetition. This is how you can amplify the sounds. And in the spirit of this talk, I'm giving you a great result, and then I'm complaining about it. So what is my complaint this time? So if you look at the length of the new witness, so the original one was of length m, maybe it's roughly linear in the original witness, but the new one goes from m to m to the k. So if you want to make this number very small, k will be large, so then you are like a PCP of length m to the 100, m to the 1000, whatever it is. In particular, this recipe will never give you something near linear because you cannot even get k is equal to 2. Okay, so that's the situation. And the question that is the focus of this talk is the following. Is there a way to amplify the soundness of a given PCP verifier while paying much less? I don't want to go from m to m to the 10. Ideally, I would like to go from m to O of m. That we don't know how to do that, seems pretty hard, but anything that is better than that would be nice, and ideally maybe only pay some logs. So that is what got started us on this journey. And if you're an optimistic person, you could have the following idea in mind. You say, okay, if I look at this parallel repetition, I can think of this as kind of applying the complete k-dimensional complex on my original witness. What do I mean? Imagine your vertices are 1 to m, and on them you have these symbols written, W1 up to Wm. That's your original witness. Now you go to k-faces. These are all of the k-sets. And now for each k-face, you just write all of the symbols associated with vertices in it. This is exactly what you get. And I'm slightly cheating, but if you look at some other proofs of parallel repetition theorem, you will see that actually the expansion properties and stuff like that about the complete complex very much help you in proving that the soundness of PCPs decay when you do that. So
This shows up already in the
No, in maybe somehow in the background, I don't know, but in slightly weaker results that still give you some decay. So Raz proof is like complete information theory. Okay, so with that in mind, if you're an optimistic person, you could say the following thing. Okay, so complete complex, the issue is that you have too many K faces. Why won't you take some sparse complex that still has some nice expansion properties and just use that instead? And
So kind of the tuples of questions that you ask are cells from this complex instead of cells from the complete complex, right?
that's what you
An idea.
that's
an optimistic idea.
yeah, that's what you would want. But let me maybe say, so I'm jumping ahead, but let's consider this PCP verifier here. So sometimes it can like query 3, location 3, and location 17. So that you can think of like as an edge. But there is no reason that your complex that you apply here would have anything to do with the edges. So you have here two completely disjoint things, like the topology of your verifier and the topology of X. So that's why it's like a very optimistic hope. But still, you know, if you're optimistic, you say, okay, I have that in mind, maybe it will work. And I think that, so Irit, maybe you'll say, so Dino Kaufman, I think they were very optimistic, and I think that this was their motivation, and they said, okay, let's forget about this PCP stuff, let's look at some combinatorial analog of this problem. This is precisely the agreement testing problem that Irit mentioned towards the end of her talk, and let's see that high-dimensional expanders are indeed good for that combinatorial problem. And what Irit and Tali prove is that if you look at close to one soundness regime, it is indeed the case. But for 1%, they couldn't do it, and they conjectured that this is achievable by some high-dimensional expanders. So I also want to highlight here the difference. So they proved that for 99%, every high-dimensional expander works, but conjectured that for 1%, some work. And this turned out to be a very precise way to put it. So when we first started working on it, we said, okay, this is maybe jumping the gun. Let's try to look at this combinatorial problem and see what's happening there. And when we got started, I didn't know anything about high-dimensional expanders. So I kind of jokingly said so Mitali Bafna was my postdoc. I kind of jokingly told her, okay, let's prove that these things don't exist. Let's show that high-dimensional expanders satisfying the Dino-Kaufman conjecture do not exist. And my plan of attack was as follows. Try to prove that some complex does satisfy the conjecture, try to derive some property of it, and show that these properties are so good to be true that they simply cannot be satisfied. So we did that, and in fact we worked out precisely necessary and sufficient conditions for the Dino-Kaufman conjecture. So that was nice, and this already told us that things here are very delicate, because these necessary conditions we already knew they are not satisfied by some high-dimensional expanders constructions. So that was already quite interesting, but we had no idea of how you even come up with complexes that satisfy these conditions. So these conditions roughly amount to having very good spectral expansion and very good co-boundary expansion properties on top of some like good understanding of the links of your complex. So fine, we worked this out, and then we didn't know what to do, so we talked to Alex. And I remember, so we emailed him, and then we set up a Zoom talk, and Alex was very nice, very generous with ideas, and told us a bunch of jokes, and it was, oh, by the way, I learned a lot of Jewish jokes from Alex. And he said, oh, by the way, I have this paper with Michael Chapman, it's going to be on archive soon. We construct something which is kind of what you need. It is. So I mean, it's quite heavy. It's above my pay grade, this construction, but yeah, that was really crucial in all of this journey. And if you fast forward 2 years from that point, so this conjecture was resolved, and eventually we also managed to lift it back to the PCP setting, and we managed to get the following result. So this result is based on a joint work with Bafna and Nikhil Vyas, together with Zhe Zheng, and it's based on previous lines of work by Dinur, Dickstein, and Alex, and by Bafna, Lifshitz, and myself. So it says the following. You can get a PCP construction with n times polylog n size and arbitrarily small soundness. So it's the same as Dinur's PCP, but you can drive the soundness to be arbitrarily small.
So U2 epsilon is that low point?
No. So you pay in the polynomial here, in the power. I actually don't know how do you pay, like how much you pay.
Epsilon to be 1 over log n of something.
So it will be like log n to some omega of 1. Yeah. So I mean, imagine there is some 1 over epsilon hiding in a degree of this polynomial. Yeah, so I'm not going to tell you all of the proof. I'm going to tell you one thing about it. It uses a bunch of things. Yes, I know most of them. Yeah, and also it's building on like very rich literature by many people sitting in this audience, and maybe I probably missed many more. So I want to tell you a little bit about the proof and about what's going on. First thing I want to tell you about is that these 3 components you've already seen, or kind of seen. So this direct product testing component, this is exactly what we talked about in the end of the talk. You have these little pieces, they have some non-trivial agreement, and you want to staple them into one global object. So that was in the previous talk. And zigzag product, I mean, you've seen in Gil's talk, and you're going to see in Avi's talk, I think, right, Avi? And but you never know. Yeah, high-dimensional expander, I don't need to tell you about it. You know more than me. So with that in mind, I want to tell you about something that was kind of unexpected to us, and that is how distributed computing type things come into the picture. And I think that this is like one additional benefit of high-dimensional expanders that I've not really seen previously. So, okay, so let me tell you about that. So, for now you can completely forget about PCPs, none of that. This is a combinatorial problem. I give you a graph G. Here it is. And I give you collections of pairs of vertices, S1, T1 up to Sm, Tm. So they're here. And the problem is each vertex Si, it has some message. It really wants to relay that message to Ti.
So I don't think of them just as sets, really Si sends to Ti, not Si sends to Tj for some pair and J or some.
Yeah, no, S1 wants to send to T1, S2 wants to send to T2. Yeah. So that's what you want to do. But the game is you can only send messages by edges of the graph. So you cannot just teleport the message from S1 to T1. You have to walk through your graph and route it. Okay. So here's the definition. We say that the graph G has an R-round protocol if, no matter what sources and targets you choose, there is a way to route the messages along the graph in at most R rounds, where in each round the vertex sends messages only to their neighbors.
A vertex can pick up from several nodes and send to several nodes.
Yeah, no, as long as they are adjacent, you can do it.
No capacity, no limit to the capacity.
So there is a limit. So I'll get to it. So, of course, if there is no limit about anything, this would just be the diameter of the graphs, because you can just get paths. So what you want to do additionally is to have small congestion. You don't want like one vertex to send too much information. Like imagine that the graph is like just a star. There is one vertex connected to everybody, so everybody sends him the message and he relays it. So that's like 2 round. But that's cheating. That's truly cheating. That's not like parallel repetition. So the game is you want your graph G to have small degree, and you want the protocol to have small congestion. And there is a very nice result. It says that if G is a spectral expander, sufficiently good, then you can do it with off log n rounds. So still diameter. Okay, so that's a very nice result and it's useful. But for us, this is not quite the correct question. So for us, if you're in an ideal scenario, you just send messages and they arrive, that's great. But in our scenario, there are corruptions. Namely, sometimes messages don't make it the same way as you intended. So what do you do about that? Okay, so let me change the game a little bit. So now I'm going to talk about vertex corruptions. So what do I mean by that? Well, after you've set up your protocol, some evil adversary can come and corrupt constant fraction of the vertices, a small constant fraction. Namely, the adversary can choose these vertices and then control whatever they send in each one of the subsequent rounds of the protocol. So in particular, if you're counting on this guy sending something to that guy, that may not be the case. And now the question is still the same. You want to construct a graph G and design protocols so that even though there are all of these corruptions, it's still the case that you manage to relay the messages from SI to TI, at least for most of the pairs.
The message can be relayed more than one way, right? That's
Yep.
the idea. Yes.
Yeah.
Now, what is the order of the quantifiers here? You have to give the protocol and then the adversary chooses the vertices?
Yeah, you choose the protocol and then the adversary chooses. Of course, right, because if I knew what is the corrupted vertices, I'm just going to avoid it. Yeah. So
The protocol is deterministic design?
I don't think that matters, but yeah, deterministic, let's say.
Is corruption like in code? You put it and then, I mean, suppose if I have like 2 roots
Mm-hmm.
from S to T, and one of them is corrupted but the other one isn't.
Mm-hmm.
So do I need to care about the fact that the corruption will give me some false?
Yeah. So corruption is completely arbitrary. It can manipulate it in a way to confuse you.
The protocol needs also to tell the end vertex how to decide out of all the messages that it got what was the original message. It needs to follow the protocol.
What if all the sources are corrupt?
Yeah, so you should imagine that M is of the order of n, like theta of n. So okay, you can corrupt some of the sources, but not all of them. So of course, if you corrupt other the source of the target can say, oh, I didn't get it. So you have to allow for that. Okay. So this problem was actually already studied in the 80s, and they managed to construct quite good networks. So they managed to get networks that have polylogarithmic degree in n and polylogarithmic walk complexity. And walk complexity is kind of, this is a technical term capturing what is the congestion. It's roughly how much computation each vertex makes throughout the protocol. And what you should take from this is that the degree is kind of small and the walk complexity is kind of balanced. So that was the model that distributed people mainly studied. I don't know why they studied it. I'm sure that they have good reasons. But for us, that's not really what we care about. We care about an even richer type of corruptions, which are edge corruptions. So let's set up this new game. So still the same setting. You have the graph, you have the sources and targets pair. You still want to relay messages. But now the adversary can come and choose a subset of the edges to be corrupted. And by that I mean, if this guy sends a message to this guy in some round, you really have no idea what's going to be the output here. The adversary can make it whatever they wish. So you can observe that this is...
The adversary has full view. I mean, he knows what the information is that anyone has gotten so far.
Yeah. I mean, okay, the adversary does it before the protocol begins, but he knows what is the protocol. Yeah. So this is a much richer type of attacks that an adversary can do. For example, if you want to simulate a vertex corruption from the previous model, all you need to do is corrupt all of the edges adjacent to this guy. And that's effectively saying, oh, I took control of this vertex.
In bounded degree graphs, it seems to be the same, right?
Yeah, that's true, that's correct. But if you notice here, so these people didn't quite know bounded degree graphs. They knew like polylogarithmic degree graphs. So there is a distinction. Okay, so that's the goal, and for some reason, I don't know why, there is like only one paper that studied this model, and I think that that's essentially what Michael said, that you can transfer vertex corruptions to edge corruptions by paying 1 over the degree factor in the tolerance factor. So that was a little bit sad for us, because we really needed this type of objects. We couldn't afford this 1 over log. So what we showed instead is that actually if you take your graph to be the underlying graph of a spectral expander, sufficiently good one, or a spectral high-dimensional expander, then you actually get this type of tolerance. You can actually find routing protocols that are tolerant against constant fraction edge corruptions. Okay.
Still interesting to construct the original model with constant degree?
Yeah, so that we did in the follow-up. So one reason I really like this model, or think that that's the correct one, is you can sort of compose routing networks, and it's kind of like in the PCP theorem, you can compose routing networks until it becomes so small that you can just do something like humongous in the degree. But I don't know how to compose it in the vertex corruption model. So, yeah. Okay. So this is now the technical part of my slides. And I'm going to try to tell you a little bit of how high-dimensional expanders are related, but I'm not going to give any formal definitions of anything. Just going to be like vibe. So an informal view of high-dimensional expanders. So what is an expander? So you know the definition of the eigenvalues, this and that. Forget about it. It's a graph that is sparse. It looks like the complete complex or the complete graph for all intents and purposes. By the same logic, what is a high-dimensional expander or spectral high-dimensional expanders? Well, it's some hypergraph. You have faces of dimension 1 to d. It's downwards closed. And for many intents and purposes, it looks like the complete complex. So let me remark that for once you go to high-dimensional expanders, there are several notions. There is this notion of spectral expansion, which is much more popular, and there is also the topological notions that Irit mentioned in her talk, which are called consistolic expansion and coboundary expansion. And it turns out that both are important for us, for this PCP application. But I'm not going to say anything about that. So let me give you a feel of what I mean by roughly looks like the complete complex, and this will build us towards this routing protocol. Okay. So I'm going to think about the d-dimensional faces just as d clicks. It's just a subset of d vertices that are a click in the graph. And the way, or one feature of high-dimensional expanders is that it's sparse, namely the number of these d-clicks is not too large, but still these clicks are well connected in a sense. And here is the well-connectedness that I'm going to care about. So let's do a walk on d-clicks that goes from a given d-click to another d-click that intersect on d over 2 vertices. So I can initiate this walk from anywhere I wish, and I can do it again and again. And my running definition, or the way I'm going to use high-dimensional expanders, is that this walk on d-clicks converges very quickly. Converges roughly in log n steps.
Why does half is important here? Like, is it important? Because the intersection
It has to be sufficiently small constant times d.
sufficiently small.
So
Yeah.
you have to think about the asymptotic. If I think about
D is
equals
large.
3
No.
through,
D is large. You should think of D as maybe like log n or log n, but it's not going to be really like that. It's good to think about it. It's going to infinity. Okay. So that's the walk. So Michael, to your question, actually need to be sufficiently small, constant times d, but not too small for reasons that will be more clear in a moment.
Clearly need to be smaller than 1/2, for example? Or half?
No, just a random constant I pick. Yeah. Yeah. Okay. So that's what I'm going to use. So how do I use that to construct a routing protocol on my graph or on my high-dimension expander? So let's do it. So I'm going to slightly change the problem. So remember, originally each vertex in the graph contains a message. You wanted to relate to some other message, to some other vertex. So now I'm going to imagine that instead of one vertex containing a message, the entire clique of vertices contain one message. This is kind of without loss of generality, but don't sweat it too much. And now your goal is to relay the message of clique D to some other clique which is far away in the graph. Okay, so that's what you want to do, and you want to do it fault-tolerantly. Namely, you want to be able to tolerate edges being not quite what you wanted them to be. And the way we're going to do it is by what we call the click-to-click routing protocol. And the idea is very simple. So if all of these vertices send their message to the next click, and the next click computes the majority of, like each vertex there computes the majority of what they got, I mean, they have much more chance to know what is the truth than not taking majority. It makes you more stable. So that's the intuition, and if you walk through it, it indeed works. So let me be a little bit more precise. So first what you need to do is, remember, you have the click D1, it wants to relay the message to some distance click D sub L. First of all, you need to find a path between them that goes through clicks. And what you do is you just find the collection of these paths, and these paths have to be roughly balanced, but that's okay. And the reason you can do that is because this walk is expanding. So that's where we use the half, or half times d, or something that is not too large times d. And now what you do is you just propagate the message of click number 1 up to click number L, one step at a time. So what you do is, in round t, you look at a click d sub t. You look at the intersection between dt and dd plus 1. That's half of the vertices. Now, each guy here sends the message to each guy in the intersection. Now, each guy in the intersection computes the majority of the values they received. This is what they are going to determine as their value. And then, each guy in the intersection is going to send their message to the following click. And of course, the following click now also does the majority computation, and
There is
that's
no check for consensus. So D2, the vertices in D2 need to agree that they all.
no. So they need to mostly agree. Like the overwhelming.
There's no stage of
Initially, there is consistency. Like in D1, originally all of the messages are the same.
But this is not verified later on.
Yeah. So what I'm claiming is that actually this process will ensure that.
The big corruption is already, as we said before, the source code that's similar to having non-agreement in the original bit, right? But you have a small,
Yeah,
like,
but
some constant amount.
yeah, but that's not too much. That's like 1% at most. Yeah. So that's the protocol. That's really all that there is to it. And how do you analyze it? So I'm not going to give you the full analysis. I'm going to give buzzwords. So you have the opinions here. Each guy sends it to the intersection. So what is the chance that the majority that this guy computes is different from the overwhelming majority before? Well, this is the over two independent opinion. It's not really independent, but still you have a chain of bounds due to Dixon and Hopkins, and you can show that each transfer is successful except with probability exponentially small in actually root D. So that's a single transfer. You have to do it L times, so it's just union bound. So overall, you succeed in this transfer with probability 1 minus L times 2 to the minus root D. And if you remember that L is roughly log, and you know like high school algebra, you just set D to be log squared, and you get something close to 1. Hmm? Outside? Okay. So it's that.
So why is there snow?
Very smart. It's not independent.
Yeah.
So here you can expect exponential decay.
Yeah. Yeah, so that's not. Yeah. Yeah.
Spirit of complaining.
So that's the click-to-click protocol. That should give you a good idea of how the routing actually works. If you actually go through this plan, I think it's successful. Like, we never worked out like, the full details, but you'll get a construction of size slightly more than I said. You'll get n times 2 to the polylog log n. To get what I said quasi-linearly, you actually need to. So the issue is that clicks are a little bit too small. So once you get the opinions, if you want the opinion to be consistent, you have to take large dimension, and then you pay. It turns out that click is not that important. What you need is a large set that has good mixing properties, and a small diameter and stuff like that. Link is as equally as good as clicks, and once you execute the same idea on links instead of clicks, it takes a little bit more work, but it does work. And it gives you quasi-linear. And actually then you don't need any chain of linear. It's just spectral bounds, nothing more than that.
Can you say something?
Hmm?
Can you say something? Why when you go from D to D2 or better? Why then?
Just because links are larger than clicks. So I can arrange for the size of the links to be polylogarithmic while still having constant dimension, but clicks I cannot. Yeah. So that is the routing component of our work. And it turns out that once you have this routing component, what you can do is you can take your PCP verifier and change the topology of the checks that he makes so that it's compatible with whatever complex you need. And once you do that, you can actually use these combinatorial versions to do amplification. So that's about our work. So after we published our paper, so we used like the construction that is number theoretic, it's building, it's all of these things, and the subsequent work by Tali, Izar, and Shmuel, and by Donald Singer showed that you can actually use a different set of complexes that are due to Kaufman and Oppenheim. These are the constant complexes, and they are equally as good, and you can go through everything that I just said, and it still works. And a work by Hopkins and Ray showed a much more down-to-earth high-dimensional construction that achieves slightly worse parameters, but still all of these ideas can be used there.
What's an elementary complex?
Just a flat, I mean, just all of the subspaces of a given FQ to the n, but with appropriate choice of parameters.
This is like
Yeah, it's the same type of parameters. It's also kind of the same idea. I mean, if you think Washkovich is plane versus point or plane versus line, stuff like that, and the complex is also talking about such things. Yeah, so then we also had two other implications of these things. So as I already said, we got better round-trip protocols that I told you, namely we have ones with constant degree, and we also have some nice applications to fix parameter complexity, but I don't want to say anything about that. So I have like 2 minutes, and I don't want to say too much more. So I'm not going to tell you about PCPs of proximity. I'll just tell you that there is something called PCPs of proximity. It's a strengthening of PCPs, where instead of asserting that a given witness is satisfying assignment or not, you want to be able to tell whether it's satisfying assignment or far from everyone. So this is this type of objects, and long story short, you can discuss them, you can discuss what is the best possible ones. Something was known, we improved it, as usual.
Sounds like research.
Yeah, but the point here is that for these PCPP constructions, we again had to observe some special property of the high-dimensional expander construction I just told you about. Observe that it has something going for it that enables better composition results. And this is really this is really the level I want to stay at. And the reason we do that is because there are error correcting codes called locally decodable codes and relaxed locally decodable codes. And it's a big story of what is the best locally decodable codes and how do they compare to the best relaxed locally decodable codes. So anyway, we had some application to that, and we showed that actually, so this is a relaxation of LDCs, as the name suggests, and we showed that it's a true relaxation. Namely, they can achieve something which LDCs cannot achieve. So skip that, blah, 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 blah. Okay, so let me summarize. So in this talk I told you about PCPs, I told you that there are PCPs, and I told you that there is some application to correcting codes, and I hope that you got the feel to the connection to high-dimensional expanders and to distributed computing. There are still some things that we don't know. So yesterday when I was finalizing my slides, I was trying to come up with questions that look more like non-TCS. And here are two. So in our construction, it's important that the complex we construct has vanishing cohomology over the symmetric group of size M, where M is sufficiently large constant. And we don't know if there is a complex that can achieve it for all SM simultaneously. I don't know of any direct application of it to TCS, but I sort of have the feel that maybe it will be useful one day. And another type of this question, so in all of the complexes that I know, the degree of each vertex is at the very least 2 to the d squared. And I would personally be very interested to know if there is like 2 to the d type degree things. Again, I don't have any concrete application for it, but maybe in the distant future there will be one. I don't know if there is any feeling of whether this should be the truth or whether there is even sparse complexes, but if you have any information about that, I would be happy to know. Lastly, there are a bunch of open problems about TCS, so I don't want to read it out loud because I'm running out of time, so I'll finish here and wish Alex happy birthday.
Question. When you say dimension of the chronology over SM, what do you mean group chronology?
So the same as the triangle, okay. The same was the triangles of the Rit, but you take product over these, and you ask, so like,
Coefficiently sum and
yeah, so instead of the map being from on F2, you map vertices to elements in SM.
Basically, you don't want to normal finite examples.
yeah, exactly.
From the lambda group will not have all the examples we have. So usually
And also question is, can you have them have like trivial profiling completion, no finite
Google Moses, for example.
actually group theoretically it's very
Any more questions? Any more questions? If not, then let's